So for those of you who missed the lecture on Monday, I'm going to recreate that circuit example that was done in class. So we'll say Vn goes through this resistance and this potentiometer and this resistance. And here's the op-amp down here. Here goes the output, V out. And put a capacitor in the parallel path here. We'll call that C. This is R1. This is also R1. And this here is R2. Now to represent the potentiometer, we're going to rewrite the potentiometer as two resistors called R2 times 1 minus alpha and R2 alpha. So this three-terminal device is a representation of the potentiometer where alpha is the percentage of the full scale of the potentiometer. So given that we have that, we can redraw this circuit in terms of some, of only resistors that are shaped like the kind that we're used to. So that redrawn circuit looks like this. V out and V in. And this is R1. This is also R1. This is R2 times 1 minus alpha. This is R2 times alpha. And this is just C, because there's only one capacitor. So then we'll do a current analysis rather than a voltage analysis, or rather than voltages, because if we take KCL at these three nodes, we can find the answer, but it's a lot cleaner if we do this in current. So we'll say here's a current here, and we'll name this current I2, and here's a current, we'll name that current I1. Actually, the other way around. This one's I1, and this one's I2. And this current will be I1 plus I2, and this current will also be I1 plus I2. Because no current flows into the op-amp, I2 can just go straight across, and I1 and I2 both have to go through both of these R1s, so this representation allows us to do our first calculation, which is the voltage across here is the same whether we go through either path, so we can write that as I2 times R2, because R2 times 1 minus alpha plus R2 times alpha is just R2. And that's equal to the voltage across the capacitor, which is going to be I1 times 1 over SC. And then we can just write that I1 is equal to I2 times R2CS. So circle that. This is going to be useful later. We can also say, because we can also find the voltage V in terms of these currents. So let's say that V in is equal to, first the voltage across R1, so we say R1 times I1 plus I2, plus the current through this resistor to this node, which is also ground, or which is also 0 volts, plus, and so we can say that that's I2 only times R2 times 1 minus alpha. And then if we put in our new value for I1, we'll get a longer value for IN or VN called R1 I2 R2CS plus I2 plus I2 R2 1 minus alpha. Grouping the currents together, we get I2 times this big quantity of R1 times R2CS plus 1 plus R2 times 1 minus alpha. And if we do the same trick for finding V out, so that's through this resistor here and through this resistor here, we find V out equal to 0 minus, everything's minus because we're moving with these currents instead of against them. So everything's going to be flipped negative. Alpha times R2I2, so that's alpha R2 times I2, minus that same R1 times I1 plus I2. We get rid of, let's make this minus sign, and then these will all be pluses. And we can get rid of our I1 the same way we did before, so we say alpha R2I2 plus now R1 times I2 R2 CS plus I2. And then grouping all of the I's together and moving that minus sign back to this side, we say I2 minus I2 times this big quantity of alpha R2 plus R1 times R2 CS plus 1. And we can now compute the big fraction h of s, which is equal to V out over V in. And since we have values for V out and V in, we can just write this fraction and get rid of the i's because they will cancel. Say minus alpha R2 plus R1 times R2CS plus 1 divided by R2 1 minus alpha plus R1 R2CS plus 1. So this actually is the transfer function, and you could certainly use this and plug this into MATLAB and see what would happen. But let's simplify this down a bit further so that we can really get a feel for what we're looking at, because this is kind of large and messy. So let's rewrite it really clearly first. Say alpha R2 plus R1 times R2 CS plus 1 divided by R2 1 minus alpha plus R1 R2 CS plus 1 again. So this fraction would look better and teach us more about the circuit if we could get S by itself in both of these. Now luckily, if we divide this fraction through by R1, R2C, then the S's will drop out. But to make that a little bit clearer, we'll just pull the S's out of that parentheses first to do that. So let's say minus sign alpha R2 plus R1 R2 CS plus R1 divided by R2 1 minus alpha plus R1 R2 CS plus R1. Now we multiply the top and bottom by 1 over R1 R2C to get alpha times 1 over R2C, or R1C, plus S plus 1 over R2C divided by 1 minus alpha over R1C plus S plus 1 over R2C. And reordering this so that we see these in direct 0 over pole form, we have S plus alpha over R1C plus 1 over R2C over S plus 1 minus alpha over R1C plus 1 over R2C. Now, what you've got here is an expression of a transfer function where you have a pole here and a 0 here.